We are back, and this time we're going to do some modeling of the systems. We will start with the modeling of first order system, going for the second order system, going for the higher order systems, and so on and so forth. And in the sequence, we'll start with the simplest one first, that is the first order system. So the first question which comes to the mind is what is a first order system? Mathematically, it is defined as whatsoever whose final model is given by first order differential equation, or you can say whose output is modeled as the first order differential equation. So as you can see over here, if I may be allowed to use a laser, that this kind of equation, anything which fits in this kind of equation will be categorized as the first order system. You know, ft is the forcing function and y is the output. Y is the output, ft is the forcing function. And since this is the first order linear differential equation, it's time invariant because this a1 is not dependent on time. We don't have anything like a square of this over here. That's why it's a first order, is because if you have only the first differential equation of the first order, that's why it's called first order differential system. It's a linear system. Now here we have to take into account one important thing, that is that if this a naught is not equal to 0, why? Because my intention is to divide the entire equation by a naught. I want to divide a1 by a naught, I want to divide this by a naught, I want to divide b by a naught. And for dividing anything, we have to have this a naught should not be equal to 0, because in some cases this a naught is equal to 0, as you'll find in the subsequent slides. But right now, as you can see, that supposing that this is not equal to 0, going by that intention, what will happen? I'm going to divide by a naught and I'm going to get this equation. And here again, what we see is that I'm going to get one coefficient like this. I'm going to brand it, give some name to it, as you'll see in this next slide. And this is another coefficient, it is, I'm going to brand it. So instead of having the idea of having three coefficients, a1, a naught and b, I have only two. I have only one something called over here and one something called over here. I'll see in the next slide. So with that intention, I have divided the whole thing by a naught, provided a naught is not equal to 0. I think things are quite simple till now. Let's move further. So as I had the intentions of calling this thing as tau p and this thing as b naught upon a naught as kp. So this entire equation, it now boils down to the simple one. I call it as tau p dy by dt plus y is equal to kp into ft. This tau p, tau, the Greek letter tau, it's the time constant. We'll see why. And this is called gain, kp. It's called gain. That also will come to know very soon why. Maybe not in this session, maybe in the next session. So what we see over here is that this tau, as I've been repeating telling you, that it's called time constant and kb is called the gain, and it's specifically called steady state gain, or sometimes it's called static gain, or it is sometimes simply called gain. As I've been telling you, it's called gain. So that's how the things go. Like, so this is the equation. So anytime and every time you come across an equation which has number one dy by dt, the first order linear thing, and then you have y, and then forcing function is there, and then you have two constants are to be taken. The first constant along with the dy by dt is taken as the time constant, and the one which is taken along with the forcing function is called gain, or static gain, or steady state gain, as you may feel like calling it comfortably. Now we introduce the concept of deviation variable. This is very important that you know what is deviation variable. Deviation variable means that uh, you have everything going in steady state. Everything is perfect. You have certain flow, you have certain input, you have certain forcing, and it's in steady. All is in steady state. You bring about a change, in the forcing function, then the output will also vary, and as it's going to vary, then we are going to start from that point onwards. We say that now we are going to say not what is the output, what is the change in output from steady state, not saying what's going to be the forcing function, but what's the change in the forcing function at steady state? Because at steady state, at t is equal to 0, the change has just begun. So at t is equal to 0, we say that in terms of deviation variables, in terms of steady state, there is no change. There is no change. It's because we cannot say that y is equal to 0 at t is equal to 0. We cannot say that t is equal to 0 is equal t is equal to 0. There is some value of y, but the idea of taking entire thing in terms of steady state is that if we take this y as in terms of what is the change from steady state. So at steady state there is no change, so at steady state the value of y0 will be equal to 0. Similarly, at steady state, at t is equal to 0, the value of forcing function at 0 t is equal to 0 will be equal to 0. And this is very important. Why it is very important? Because ultimately my aim is to go to get the transfer function, and you know the definition of transfer function is that whatsoever is the Laplace of output divided by Laplace of input functions, assuming all initial conditions to be 0. If I do not take it in terms of steady state, the deviation from the steady state, then this will never be equal to 0. This also may not be 0. So in order to bring this to 0 and this to 0, so that I can ultimately take the transfer function where the requirement is that I have to take these initial conditions to be 0, it becomes almost a compulsion for me to take all those things in terms of deviation variables. So this is the reason we go in for deviation variables. I may not repeat this again and again in the subsequent sessions, but we have to keep it in mind that whenever we want to take any transfer function, whether for the first order system or for the second order system or for whatsoever, we have to go in for these deviation variables so that these two conditions are fulfilled, and with these two conditions being fulfilled, we can easily go in for taking the transfer function. This is the basic concept, and this is what I'm going to even show you here. Here it is that why do we take it in terms of deviation variables? Why not simply in let us say we call it as new. So new is, or v, or whatsoever you may call it, v is the full value variable and vss is the nominal value of the variable. And if I subtract the two, then the idea is that we call it as v star. So v star is taken as the deviation variable, and at steady state this v is equal to vss, because this v is equal to vss, so v minus vss at steady state will be equal to 0, and this is going to lead to this result. So this is what we call it in terms of steady state variables. In terms of deviation variables, we take everything in terms of deviation variables, and deviation is taken from the steady state. So this is the idea or the philosophy behind taking all the deviation variables so as to fulfill this requirement, so as to go in for Laplace transform or the transfer function. So once again, when we go in for the deviation variables, we have a tendency to put a bar over here, and when we put a bar over here, we get ys bar over fs bar. This comes out to be equal to kp upon tau ps plus 1. You all know why, because tau p multiplied by dv by dt dy by dt, that the deviation in terms of deviation variables, the initial condition is always 0, so you don't have to subtract anything from here. And whenever you take Laplace of dy by dt, it gets multiplied by s. So this tau p is multiplied by s plus y. As such, it was the form of something attached to here. It comes down, and this kp के साथ लगा हुआ था fs, so this fs comes down over here, and ultimately if you see, we get this simple equation for the first order equation or for the first order system. So this is, we have already gone in for one model of the first order system, and we have number of things to be understood from this equation. The first thing we would like to say is that this first order system is also known as first order lag, linear lag, or exponential transfer lag. Why do we put the term lag over here? because there is a lag of time constant tau p. Things are not going to increase immediately. We'll see in the next session something about when we talk of the dynamics of first order system. This is the reason we call it as first order lag. Second thing is that in case we take a naught is equal to 0, in that equation we take a naught equal to 0, and in that case if you see this equation becomes dy by dt, as you can see over here, this becomes b upon a1 into ft, and because a naught is equal to 0, so this thing b upon a1, this thing b upon a1, I call it as the gain, but to distinguish it from the previous gain, because I have now divided by a1. In the last case it was divided by a naught, so here we are divided by a1, b upon a1. This is not called kp, this is called k dash p. So the effect is that if I take the Laplace, then what I'll get over here is y in terms of deviation variable will get multiplied by s because of the term that we have dy by dt, and the forcing function is anyway f, so this y comes with a bar over here and f comes with a bar over here, indicating that this is also in deviation terms. This is also in terms of deviation variables. So once again, once we go in for that, with initial conditions will automatically become 0, and you will get the transfer function of this equation where a naught is equal to 0. This will become k dash p upon s. My dear friends, compare it with this one. I cannot put tau p is equal to 0 directly. I cannot, right? And we have to see that in case a naught is equal to 0, this entire thing comes out to be this. It's all in front of you step by step, and we get this as the transfer function. Compare it with this one. You see, this one is called pure capacitive, and if you take its Laplace inverse, so 1 upon s means integrator. I think you all know that in case you have differential equation, and whatsoever you have the dy by dt, you take its Laplace, it gets multiplied by s, and in case you have integral of anything, you get 1 upon s, and this term is 1 upon s. That's why it is also called pure integrator. We will see in the dynamic response once again, but right now you can say that this kind of terms are known as pure capacitive. These kind of processes where you do not have any tau p over here, and the response is given by this, specifically where the equation is having a naught is equal to 0, they are called pure capacitive, or they are called pure integrators. So we will take some practical examples of how the various physical systems can be modeled as the first order system. In most of the cases it's some kind of storage and some kind of resistance. That's what we're going to see in the subsequent slides. So as I said, we have to model some of the processes as first order systems. There are two things. Number one, there has to be some capacity to store. This is what I told you earlier, capacity to store the material. And number two, there has to be some resistance associated with the flow. This flow can be flow of mass, flow of energy, or flow of momentum, any of the three. So I'll be focusing mostly on the mass part because it's easy to visualize for you. You can see the mass flowing. Although temperatures and all can also be used to know the flow of energy, but we'll keep things simple to start with. So the resistance which is associated with the mass flow is one thing, and the capacity to store is another thing. Once these two things are available, then in that case the model can be processed as a first order system, and that's what we're going to see now. As I said, wherever you see a tank, wherever you see a tank, and wherever you see some resistance in terms of valve, in terms of weir, in terms of pipe, which gives the resistance to the flow, you can easily model it in terms of first order system. Similarly, wherever you can store some energy, here thermal capacity is there, so you can store energy, and there is some flow of heat through walls or through whatsoever manner. Heat exchanger has basically walls only through which the energy is flowing, and so on and so forth. These can also be taken as first order system. So the things related to the tank heaters and the mixers and so on and so forth, they can be the simple typical examples of first order system. This is what we have seen so far. So this is what's symbolized over here. So wheresoever you have some tank and you have some flow and you have some resistance to the flow, so whatsoever is happening, it can easily be modeled as the first order system. So we start with the first example of first order system, and what you have here is again a tank. The tank has area of cross section A. The tank has level H. The tank has some inflow Fi, and the tank output is F naught. And the thing to be noted very, very carefully is that this F naught is actually dependent on two things: the hydraulic head or the hydraulic pressure and the resistance of the wall. This is some restriction. If it's a wall, the opening of the wall is fixed for the time being, it's fixed, right? So this R is fixed. So this F naught is equal to H upon R. This F naught is equal to H upon R. So as this H decreases, it goes down. This F naught also decreases, right? And the inflow Fi, that inflow can be taken as the forcing function. What if there is a step change in Fi from the steady state? So that kind of stuff can be taken in Fi. That can become the forcing function, and the output is H. The output is H. The level is H. So let's see if it can be modeled as the first order system or not. Let's model it and see whether it comes out to be first order or not. So all we have to do is I've already told you that F naught is equal to H upon R, which H is the hydraulic pressure, the driving force for the flow, and R is the resistance of the flow, which is supposed to be constant. And what is the mass? What is the mass flow rate? I'm assuming density to be constant. So mass flow rate is same as the volume flow rate. So what is volume flow rate? Volume flow rate is given by whatsoever is Fi going in minus whatsoever is Fi coming out should be equal to the rate of change of volume. H into A is volume, and A is constant. A is area of cross section is constant. It gets out from this equation. So the rate of accumulation of volume, that is A into dH by dt, that comes out to be equal to Fi minus F naught. And this F naught, as we have seen over here, this F naught can be replaced by H over R. So this entire equation as such, which is A dH by dt is equal to Fi minus H upon R. It can be rewritten as, if you can just imagine that A into dH by dt plus H by R is equal to Fi. This is as simple as that. This is nothing but a first order equation as we had seen. So I can take this R and multiply over there, and you will get A into R is equal to dH by dt plus H is equal to R into Fi. So I'm just multiplied the whole thing by R. The idea of doing entire thing is that I get something very similar to what I'm familiar with, that you have something over here, we will call it as time constant, and there's something over here, we call it as gain or static gain or steady state gain, whatsoever you want to call it. So this is very similar to whatsoever you studied just a few minutes back. And this entire thing, of course, it's written once again, it's reiterated that this A is area of cross section. This is the equation, you just keep it in your mind. This represents first order system, where this will become the tau and this will become k. Let's see what happens in the next slide. So once again, we take the steady state value of H, we take the steady state value of Fi. So everything in turn is written in terms of uh, steady state values. So you will get everything in terms of deviation variables, where deviation means where h dash is actually is equal to h minus hs, and f I dash is equal to fi minus fs, and it is taken so that h dash at 0 becomes equal to 0. Fi dash at 0 becomes 0. Why? Because Fi is equal to Fis at t is equal to 0. So at t is equal to 0, Fi minus Fis will become 0. So is the case with h minus s. So that's what we see. We take all these things simply to make these things at time t is equal to 0 when we bring about the change at steady state in forcing function. So that's the point where we take this h dash to be equal to 0 and fi dash to be equal to 0. And of course, as I had in my mind that this AR I'll be taking it as tau p and this R I'll be taking it as kp. So this entire thing will become, this thing will become kp into dh dash upon dt plus dh dash is equal to k times or kp times f dash. So if I take the Laplace, what will happen? This thing will become tau p, and this also get multiplied by s, because you know have your differential equation over here, and this will be simply 1 is equal to, this will be kp into fi. So taking this h dash upon fi dash, I will again have the same equation as we had earlier, that is kp upon tau ps plus 1. It means that it's a first order system, and here we see that the time constant is dependent on two things, the area of cross section as well as the resistance of the flow, whereas the steady state gain is dependent only on one thing, that is the r. This is what we come to the conclusion right now. So the first thing is that area of cross section A is the measure of capacity of to store the tank. So larger is the value of A, larger is the storage capacity of the tank. And secondly, this time constant, as we have capacity into resistance, as normally we have been seeing in terms of LCR of the electrical circuits also, there also time constant was equal to C into R. Instead of C we have A over here, that's only difference. So in general we can say that time constant is equal to storage capacity into resistance of or resistance to the flow. So this is modeling of the first order system as such, where if you remember A naught is not equal to 0. This is the first case, and now we'll take the second case where A naught was equal to 0. We will call it by some different name as the time comes. I'll show it to you in the next slide. Now, my dear friends, this is something similar to what you have done earlier, but with the fact that earlier this F naught was equal to H upon R. So as this H decreased, this F naught also decreased because there was a fixed resistance R over here. But this is a different case. In this case, this F naught is equal to constant. This F naught is not dependent on H. This F naught will remain same. Whatsoever may be the value of tank, tank may be full, tank may be half full, tank may be nearly empty, this F naught is going to remain the same. It's constant throughout. That's why you see why it is called pure capacitive is something we'll get to know later when we see the dynamics. But right now, as you can say that over here, what will be the equation? Equation will be the same. What was that? A into dh by dt is equal to fi minus f naught. But this f naught is not equal to h upon r. This f naught is constant. And since this f naught is constant, there cannot be any deviation in this f naught. Once you go in for the deviation variables, there is no deviation f naught. So in terms of deviation variables, this f naught dash will be 0. Anything deviation of anything in terms of whatsoever is constant will be 0. Constants do not vary. That's what you're going to keep in mind. And with this thing in mind, let's see what happens. Again, as I said, a into ds by dt is equal to fi minus f naught, and at steady state we see that the meaning of steady state is that the whole thing is fixed, there is no change, whatsoever is input is output, and so on and so forth. So we take this in terms of steady state. So at this steady state, this dh by dt will be equal to 0. You will get this as the equation. And further, if we see that this in terms of deviation variables will be this in terms of deviation variables will be this, but since this is constant, this is what the meaning of pump is going to give it a constant flow over here. So this f naught is in terms of deviation variable becomes 0. There is no deviation in things which are constant. And once we have this, this becomes the same equation where a naught was equal to 0. If you remember, the a naught is equal to 0. So what we have over here, we take the Laplace of this. Laplace of this means that along with a you will have s, and this f naught. What you have ultimately is that, because you are taking everything in terms of standard at the steady state. So the advantage of doing this is that at t is equal to 0, the steady state value, the initial values are 0. So the transfer function of this comes out to be this a goes in denominator, this fi dash, it comes over here in denominator, and the s which was there because of the differential of this equation, ultimately it becomes 1 upon a into divided by s, or you can simply call it as 1 upon as also. 1 upon as is also equally good, but this looks fine, as over here we need something in the numerator, we need to have something in the denominator, and since you have only s in the denominator, it's a pure integrator. You have only s, you can simply take its Laplace inverse, you will get pure integration. And because it's a pure integrator, that's why it is called pure capacitive systems. These are called pure capacitive systems because over here we do not have any resistance. That's why you only have the storage. You have the storage, you don't have any resistance, so that's why it's only the pure capacitive systems. I think that should be an ample case for you to understand how do we model the first order systems in terms of the ones which have a capacitance and resistance, and those also which are not having any resistance but they are just having pure capacitive systems. This was all about the modeling. We will take the dynamic response of these two cases in the next session, and maybe take some more examples thereafter to know about the modeling related to the first order systems. In case you have any queries, you can ask me or contact me through WhatsApp or Zoom or telephones or cell phones or whatsoever means we have face-to-face interaction, and so on and so forth. I thank you for being with me, and I wish you a safe stay. Enjoy learning. Bye bye.